Oh, what are we going to do when the charges are everywhere? Okay, so this is AP Physics C, E&M content. And what we're going to start looking at are how can we get the electric field due to a continuous charge distribution. So instead of having charges just like here's a point charge and here's a point charge, what's the E field out here? What we're going to do this time is say, hey, I have an arc of charge. What's the E field out here at a point? And that's like kind of weird, right? Because this entire charge distribution here might have some charge like positive Q. How do we get this electric field? What's going on here? Well, here's how we're going to go about doing it. We're going to use a little bit of calculus and a little bit of clever thinking to get some stuff. What we're going to set up here is if this is a arc of charge, so this is a uniform arc distribution or a uniform charge distribution in an arc, and it has some radial position r, and all of this is set up so that it's a circular arc and all of it is radial r away, which is nice for us. Here's how we're going to do this. What we can initially think about is that, and you see me already tilting my head to think about this, is that each little bit of distance on this arc has a tiny bit of charge on it, dq. Okay, remember, if we have something, we can call it like q, that's a charge, but if we've got like a tiny bit of it, an infinitesimal little piece, like we've sliced up the pumpkin roll so thin, we can call this dq. Okay, now, it's like Dairy Queen. Now, I don't want to add up all of these dq's. What I'm trying to actually get is, what is my electric field out here? What is my electric field at the point? So what's a better thing to do is to recognize that, hey, look, all of these tiny bits of dq, all these tiny infinitesimal segments of charge, they give me a tiny little bit of an electric field. So if this is some electric field, what I'm going to get out of it is some tiny bit of electric field. And if I'm able to activate fancy addition, and if I'm able to add up all of these electric fields, then I'll get the electric field at that point, which is what we're looking for, and the problem's over. So congratulations to us, we did it. Now, how do I go about this? Well, one of the things we can recognize is that we know how this charge is going to create an electric field. And we know that an electric field is equal to kq over r squared, and maybe a better way to write this is going to be 1 over 4 pi epsilon naught. Remember, 1 over 4 pi epsilon naught is just the value k. Now that we're doing things in a calculus based, this 1 over 4 pi eps naught is actually a nice way of writing things. Later on we'll see how a lot of stuff's going to cancel out with it, so let's get into that habit right now. And then instead of having q's, well, we're going to have a q here and then over r squared. So if we just want a tiny little bit of E field, we can say that, hey, look, the tiny little bit of E field, dE, is equal to, well, we still just have 1 over 4 pi eps naught. And what's the tiny little something creating this tiny little E field? Well, it's the dq right here. So dq over r squared. So this is what we actually want to be integrating, because if I can integrate or fancy add this, then I'll be good. And if I look at this here, 1 over 4 pi eps naught is a constant, so it can sit outside the integral. So this is kind of what I want here. But what exactly am I integrating over? Like, what are my bounds here? How do I actually add up dq's? Like, that's kind of a weird thing to think about. So if you watch the prior video to this, you'll know that adding up things like dq, that's not a good idea. What's much better for us is to add things like to sum up densities or distances in this regard. So if we can sum up distances, that will really, really help us out. So if we take a look at this charge distribution here, we know it has some charge q across all of it, but we can also think that, hey, look, this entire curve here, it has some length, right? Like this entire thing has a length to it. Or we can call it like some curve, some path, s, whatever, but it's got a length here. And what this means is that it has some charge density. If we say, this plus q over the length, whatever it is, this is equal to some charge density. And because it's a line here, it's a line of charge. Yes, it's a curved line, but a line nonetheless. Then this is a linear charge density lambda. Okay, so this is a linear charge density. So it's some amount of charge per length. Okay, so if we think about this linear charge density, well, what I want to try to figure out is in this small little dq, that tiny bit of charge, well, how do I get a dq? What is that? Well, a dq is based off of the charge density multiplied by this tiny bit of length of that ring. So we can call this like dl or ds. Okay, I'm going to call it dl here. So if I have this tiny bit of dl here, and I multiply it by some charge density, that's going to give me my tiny bit of charge. But what is this tiny bit dl? And this is where things start to get kind of weird. What we can remember is that if we have a curve or an arc, and it's a circular arc in our case, then I know that if this was some arc length L or S, I know that this is given to me by r theta. And you might be thinking to yourself, like, Coach Botzer, how am I supposed to know that? That's a bunch of nonsense. How did you get that? Well, you already know that if you take a circle, what's the circumference of a circle? Well, it's 2 pi r, right? So what I'm really saying is that the arc length of a circle is equal to an angle 2 pi multiplied by a radius. Yeah, you knew that. So if you just want a small subsection of that circle, that angle is going to change. It's going to be some different angle that exists here, okay? But in the end, we still have the same equation, r theta. So if I don't want L equals r theta, I want this dl up here, a small segment of it, then what I can say is that dl equals r d theta. It's the same radial distance, but it's a very, very small, little, teeny, tiny angle that we're playing with, okay? So this can be thrown up for dl, which means that dq is now going to equal r lambda d theta. And why is that so helpful for us? Well, because this d theta, we can integrate over that. That isn't some weird dq value. That's an angle. I can integrate over an angle. That's allowed via the world of calculus. So let's take this r theta, or this r lambda d theta, and let's put it up for dq, for this integrand. So this is going to equal here, and we're going to keep our 1 over 4 pi epsilon naught times the integrand of r lambda, there's our lambda, d theta over r squared. Okay, and we get a few nice things out of this. We see one of the r's goes away. Okay, and since this r is a constant right here, we can actually pull that r out, so that this will now become 1 over 4 pi epsilon naught r times the integral of lambda d theta. And if you're looking at this, you might be like, well, that's kind of like a weird thing to integrate. It's just d theta, because this lambda is a constant too. This lambda should actually be pulled outside, right? Because we have a uniform charge distribution, that lambda is going to be pulled out here. Okay, if that was non-uniform, then things would get weird, and that's for college. But it's just an integral d theta. That seems a little easy, right? Well, there's one little catch here. If we take a look at our original arc, let's take a look at the bottom here and the top. If I take a look at the bottom, this bottom is going to give me an electric field pointing in this direction. The top is going to give me an electric field pointing in this direction. Now, while these aren't equal and opposite, there are equal and opposite components to them, because the top is going to give me an x component, which is the same as the bottom, but we see that their vertical components cancel out. So actually, due to symmetry, don't care about the vertical components at all. I only care about the x components here. And that's a very nice thing, because these electric fields are vectors. And since they're vectors, I'd have to like carefully add up everything in their direction and then add them with their vector components, which is a mess. But because of the symmetry here, I don't need to worry about that. The y components cancel out. the only thing I need to worry about is the x components. And if we do some little bit of mathematics here, we see that if this is an electric field or a piece of an electric field, dE, then the only thing I care about is the x component of that, which underneath here, if this is the same theta, well, we'll see that in a second, this is just the dE in the x component, which is just dE times the cosine of whatever that angle theta is right here, okay, on the inside. Whatever this angle theta is, that'll be that theta there. So this is a nice thing, and what this means is that when I start looking at this, you know, I'm kind of like stuck here, but you know, what I really want here isn't dE, I want dE in the x direction, which means that there is a cosine of theta term that has actually been following us around the whole time. And this is really cool because now I have cosine of theta d theta, and that's integrating. So kind of a neat thing. When we think about what this angle is on the inside, we can generate it by saying, look, let's cut this in half right here, such that the arc goes down some angle theta, and the arc goes up due to symmetry, some equal amount theta. That means that this theta and this theta, they are, I don't know, what would you call that? Interior angles or something like that that match up. Some geometry term I cannot remember, but those angles are the same. So now here, whenever we put our bounds on, which we didn't know before, our bounds can just go from negative theta to positive theta. And I just need to take the integral here of cosine d theta. And in doing so, I'm going to get, here's my lambda over 4 pi r. So lambda over 4 pi epsilon naught r. And the integral of cosine is just sine. So what I can do here is I can say this is just equal to sine of theta, and then this is bounded from positive theta to negative theta. So now whenever I go and I put in my upper bounds, so I put in my upper bounds and then subtract it from the lower bounds, I'm going to result in this. I'm going to get a lambda over 4 pi epsilon naught r times, this is going to be the sine of theta minus the sine of negative theta. And there's a neat little sine rule here. If you have the sine of a negative angle, you can bring that negative out and turn this positive. So sine of theta plus sine of theta is just 2 sine theta, which means that I can actually write this completely at the end as saying 2 lambda over 4 pi epsilon naught r times the sine of theta. Okay, and yes, if you wanted to, you could, you know, reduce the 2 and the 4 so that we just get a 2 in the denominator. But that will be it. That will be your electric field at some point, you know, a radial distance away from your arc of charge, you know, given by a full integral method. Okay, so it's a kind of neat thing here. The big thing to recognize when you're doing this is that you need to start off with this idea like, hey, we need to add up all these tiny bits of an electric field. So we're looking at this up here in green, like, you know, I need to add up all my electric fields. Well, how do I get my electric fields? Well, I get them by tiny bits of charges one at a time. Due to the symmetry of the problem, we only need the cosine components of those charges. And I don't want to add up charges, I want to add up distances or angles. And in doing so, we went and got some linear density amount. We were able to plug that into our equation here to get our d theta. That allows us to integrate the cosine component, and then allows us to just work down and get our final answer. Okay, so now this screen is a complete mess. Hopefully your work looks a little bit more neat and tidy than mine does. But as you do these a few times, like, you'll start to see the pattern here. You know, you're looking for E fields, you do it with charges, integrate over lengths, and then see what you get. Okay, so this first little foray into the world of integral calculus and physics combination is finished. We've got a lot more examples to do within this entire unit. We've got a lot more AP Physics C example problems that, you know, as you're trying to get more practice with this, I'll walk you through them. So make sure you keep checking out these videos and getting the help you need. But until next time, adios, and you all take it easy. Bye-bye.